Was our entire cosmic fate sealed in its first heartbeat? At the universe's 1-second birthday, a searing hot sea of particles churned in the darkness. The grand structures we know today, from swirling galaxies to the planet beneath our feet, did not yet exist. Yet in that primordial furnace, the blueprints for everything may have already been drawn. This is a journey to the very edge of what we know, where the rigid laws of physics meet the ghostly rules of quantum chance. By the end, you will understand not just how our universe was built, but whether its astonishing story was the only one that could ever have been told. We will probe a moment when time itself was infant to see if the seeds of destiny were planted then. What does it mean for our place in the cosmos if our existence was written into the first lines of creation? To find that 1-second mark, we must first step back into a realm that defies every intuition. Before the first tick of the cosmic clock, there existed a duration so brief it has no name in human experience. This is the Planck epoch, the universe's opening act, lasting from time 0 until 10 to the power of -43 seconds. In that fleeting instant, the cosmos was smaller than a single atom, denser than anything we can create, and hotter than any number has meaning. Here, the familiar rules dissolve. Gravity, the force that sculpts galaxies, was not a separate entity. It was merged seamlessly with the electromagnetic force and the nuclear forces into a single, sublime superforce. This was a state of perfect, chaotic unity. Reality itself was a seething ocean of quantum foam, where space and time did not flow smoothly but churned and bubbled like a boiling pot. In this primordial frenzy, the very laws of physics as we know them were not yet set in stone. They were in flux, a set of possibilities waiting to be chosen. It was a canvas of pure potential, where every fluctuation held the seed of a different future universe. The critical decisions that would dictate the size, shape, and ultimate fate of everything were being made in this incomprehensible storm. What emerged from that chaos would set an unalterable course for reality, leading directly to the moment 1 second later where our specific story truly began. Then something monumental happened. At around 10 to the power of -43 seconds, the universe cooled just enough for a fundamental divorce to occur. Gravity, the architect of cosmic structure, peeled away from the unified superforce. This was the first and most profound symmetry breaking, a pivotal fork in the road where one kind of physics became two. With gravity's departure, the very fabric of space-time as we understand it crystallized into existence. Before this moment, the concepts of here and there, of before and after, were blurred in the quantum foam. Now the stage itself was set. This separation did more than just define space and time. It began locking in the fundamental constants of nature. The strength of gravity, the speed of light, the value of Planck's constant. These are not arbitrary numbers we simply measured later. They are the direct legacy of that first split. Their values were determined by how the field settled as the universe expanded and cooled in those first instants. Think of it like a vast cosmic wheel of fortune spinning with infinite possibilities during the Planck epoch. At that 10 to the -43 second mark, the wheel gave its first decisive click. It didn't land on a single number, but it eliminated entire categories of outcomes. A universe where gravity is 1 billion times stronger, crushing any complexity before it begins, was now off the table. A reality where the speed of light is a sluggish crawl, making chemical bonds impossible, was ruled out. The range of possible universes narrowed from a dizzying infinity of pure potential to a still unimaginably vast, but now constrained, set of plausible realities. The laws that would govern every star, planet, and particle for the next 13.8 billion years were receiving their first indelible draft. This sudden cooling triggered an event of such staggering violence it makes every explosion since look like a gentle sigh. In a sliver of time almost too brief to conceive, from about 10 to the negative 36 seconds to 10 to the negative 32 seconds, the infant universe underwent a growth spurt of impossible proportions. This is cosmic inflation, a period of exponential expansion where space itself stretched faster than the speed of light. Picture a single microscopic grain of sand. In less than the blink of an eye, that grain inflates to become larger than our entire observable universe today. That is the scale of the transformation. During this furious burst, the entire cosmos we can see, and vastly more beyond it, was inflated from a region smaller than a proton. But inflation did far more than just make space big. It performed a critical act of cosmic embroidery. The quantum foam of the Planck epoch, that seething broth of uncertainty, was not smoothed away. Instead, inflation stretched those tiny, random quantum fluctuations in energy. What were once subatomic ripples governed by pure chance were blown up to astronomical size. These stretched wrinkles in the fabric of spacetime became the gravitational seeds for everything to come. The slightly denser patches would, over billions of years, pull in more matter through gravity, eventually growing into galaxies, clusters, and the vast cosmic web. The slightly less dense patches would become the great voids between them. So the entire large-scale architecture of our universe, the glittering cities of stars and the dark, empty highways between them, owes its origin to these quantum tremors. And here is the crucial point: the pattern of those seeds was not preordained by any law. It was frozen into the cosmos by a random quantum roll of the dice during that explosive inflation. The specific arrangement of galaxies we see from Earth, the fact that our Milky Way is where it is, even the very existence of our solar system in this particular corner of space, all trace back to a moment of fundamental randomness. The universe had written its foundational blueprint, but it did so with a hand guided by chance. That random blueprint, however, was still missing the most crucial ingredient for our existence, the stuff of stars and of us. As the universe continued to expand and cool from its inflationary frenzy, it entered a new phase of searing heat, now filled with a nearly perfect symmetric soup. For every particle of matter created in the furious energy of the early cosmos, a matching particle of antimatter was also born. Matter and antimatter are perfect opposites in nearly every way, and when they meet, they annihilate each other in a flash of pure energy. In a perfectly symmetric universe, that is exactly what should have happened. Every quark should have met its antiquark, every electron its positron, and they all should have vanished into radiation, leaving behind a cold, empty cosmos of light with nothing to build on. Yet here we are, made of matter, in a universe filled with galaxies made of matter. Something had to break that perfect symmetry, and it happened in a fleeting window of opportunity around the time the universe was just 1 microsecond old. This process is called baryogenesis, the genesis of baryonic matter, the protons and neutrons that form atomic nuclei. The physicist Andrei Sakharov outlined 3 conditions required for this to happen. The universe needed a process that violated the conservation of baryon number, meaning it could create more matter than antimatter. It needed to violate something called CP symmetry, which is a very specific kind of charge and parity symmetry that essentially governs how reactions mirror themselves. And all of this had to happen out of thermal equilibrium, meaning the universe was changing so rapidly that the process could not simply reverse itself. Remarkably, the hot, expanding early universe provided the perfect stage for all 3 conditions to be met. Through processes we are still working to pin down, involving exotic, heavy particles decaying in those first moments, a tiny, almost negligible bias was introduced. For every 1 billion pairs of matter and antimatter particles that annihilated as expected, a single, solitary matter particle was left over. 1 in a billion survived the mutual destruction. That is the source of every atom in your body, every planet, every star. This was not a designed outcome or a guaranteed result of the laws of physics. It was a stochastic tilt, a probabilistic lean in one direction over another, like a coin landing on its edge and then ever so slowly falling to one side. Had that coin fallen the other way with a slight excess of antimatter, we would have an antimatter universe which from a physics perspective is just as valid. But had there been no tilt at all, perfect symmetry, the result would have been far more barren. A universe of pure radiation expanding forever into darkness with no atoms, no chemistry, no light from stars, and no one to wonder about its origin. The fact that we exist to ask this question hinges on that 1 in a billion chance being realized in our particular cosmic story. This 1 in a billion asymmetry set the stage for the next great act of cosmic construction. By the time the universe celebrated its first true birthday, 1 single second after the Big Bang, it had cooled to a temperature of about 10 billion degrees. The era of exotic particle creation and annihilation was over. What remained was a hot, dense, blindingly bright primordial soup, a plasma so thick that light could not travel freely. Its primary ingredients were the survivors, the building blocks of all future atoms, protons and neutrons, swimming in a sea of electrons and photons. The universe was now a nuclear reactor of unimaginable scale, and the furnaces were about to ignite. This is the moment of Big Bang Nucleosynthesis, the forging of the very first atomic nuclei. The process was governed by a simple, brutal logic. At these immense temperatures, protons and neutrons were constantly smashing into each other with tremendous energy. If they collided just right, they could stick together, forming the nucleus of a heavier element, but the intense heat of the photon sea was a relentless enemy. Any newly formed nucleus would almost immediately be blasted apart by a high-energy photon, a process called photodisintegration. It was a furious tug of war between construction and destruction. The outcome of this battle was not left to chance. It was dictated by numbers that had been fixed in the universe's first instance, the fundamental constants of nature. The strength of the strong nuclear force which glues protons and neutrons together determined how likely they were to stick during a collision. The tiny mass difference between a neutron and a proton, a mere fraction of a percent, was even more critical. This small imbalance meant free neutrons were slightly heavier and thus unstable. Left alone, a free neutron will decay into a proton, an electron, and an antineutrino with a half-life of about 10 minutes. In the frantic first minutes of the universe, this clock was ticking. The expansion rate of the cosmos, itself set by the density of matter and radiation and the strength of gravity, acted as the ultimate referee. As the universe expanded, it cooled. The moment the temperature dropped low enough that the average photon no longer had the energy to shatter a deuterium nucleus, a simple bound state of 1 proton and 1 neutron, the balance of power shifted decisively. Construction 1. Once deuterium could survive, it served as a stepping stone. It readily captured another proton or neutron, forming helium-3 or tritium, which then quickly fused into the supremely stable nucleus of helium-4. This chain reaction, from protons to deuterium to helium, was an inevitable chemical cascade given the constants that were already in place. The physics was so straightforward and the conditions so uniform that the process was, in principle, perfectly predictable. If you knew the constants, the expansion rate, and the density of matter at 1 second old, you could calculate with extraordinary precision how much of each light element would be cooked in that primordial furnace. The universe was running a recipe where every ingredient and cooking temperature had been measured and locked in long before. At precisely 1 second old, the cosmos became a clockwork furnace. Its temperature hovered around 10 billion Kelvin, and its density, astonishingly, was comparable to liquid water across the entire observable universe. Within this searing, uniform bath, a silent but decisive transition had just occurred. The delicate balance between protons and neutrons, which had been maintained by a constant frenzy of weak nuclear interactions, was suddenly broken. The universe was expanding and cooling too rapidly for those balancing acts to keep up. Like a snapshot taken in an instant, the neutron-to-proton ratio froze out, solidifying at about 1 neutron for every 7 protons. This number was not random. It was the direct, calculable outcome of the expansion rate and the temperature drop over that first second, physics that had been set in motion by the earlier separation of forces and the end of inflation. With that ratio now locked in as an immutable initial condition, the fate of the primordial elements was effectively sealed. The universe had provided the exact count of nuclear building blocks, and the recipe for their combination was written into the fundamental constants. From this moment forward, the creation of the first atomic nuclei was not a matter of chance, but of inevitable nuclear arithmetic, waiting only for the temperature to drop just a little bit more to begin. With the neutron count now fixed, the universe's first chemistry experiment began its final countdown. Over the next few minutes, from about 1 second to roughly 3 minutes old, the cosmos executed a sequence of nuclear reactions with the precision of a master clockmaker. This was Big Bang Nucleosynthesis in action. Given the locked-in ratio of 1 neutron for every 7 protons and the known strengths of the nuclear forces, the outcome was almost a foregone conclusion. Nearly all the available neutrons, which are unstable and would decay if left alone, were rapidly captured to form the nuclei of the lightest elements. The first and most critical step was the formation of deuterium, a heavy isotope of hydrogen consisting of 1 proton bound to 1 neutron. Once the temperature dropped below about 1 billion degrees, photons could no longer blast these fragile pairs apart. Deuterium became stable, acting as a crucial bottleneck. Once that bottleneck opened, the nuclear chain reaction proceeded with breathtaking speed. Deuterium nuclei collided and fused, creating helium-3 and tritium, which then combined almost instantly into the incredibly stable nucleus of helium-4. Each helium-4 nucleus contains 2 protons and 2 neutrons, perfectly using up the available neutron inventory. With the neutrons all safely bound inside helium, the reaction essentially shut down. The universe was still hot, but it was expanding and thinning too quickly to build anything heavier in significant amounts. Only trace amounts of lithium-7, the third lightest element, could be forged. The rest of the protons, which outnumbered neutrons 7-1, remained solitary. They would become the nuclei of hydrogen, the simplest and most abundant element in the cosmos. So what was the final tally from this 3-minute forge? By mass, about 75% hydrogen and 25% helium, with mere traces of deuterium, helium-3, and lithium. This is not a rough estimate. It is a precise prediction that flows directly from the physics of a hot, dense, expanding universe starting from that 1-second-old snapshot. And this prediction matches with spectacular accuracy what we actually observe in the most ancient, pristine corners of our universe. When we look at old stars, at distant clouds of gas untouched by later stellar furnaces, we see that exact primordial mix. The observed abundance of deuterium, in particular, is an exquisitely sensitive probe. It acts like a cosmic barometer, reading the density of ordinary matter in that early soup. The fact that our predictions based on the 1-second conditions align perfectly with real-world observation is one of the towering triumphs of modern cosmology. For a hypothetical observer existing at that 1-second mark, equipped with perfect knowledge of the laws of nuclear physics, the future was already clear. They could have calculated with remarkable confidence the exact chemical composition of the universe to come. The recipe for the cosmic starter kit, the hydrogen and helium that would fuel the first stars, was not just likely. It was, given the constants and conditions, essentially inevitable. The universe had manufactured its raw materials on a strict, unyielding schedule. This astonishing predictability, however, has a crucial limit. To declare our universe inevitable at 1 second old, we must ask a more precise question. What exactly was already locked in? The answer requires us to separate two profoundly different things: the unchanging laws of the game and the specific starting position on the board. The laws of physics themselves, the rules governing gravity, nuclear forces, and electromagnetism, appear to be universal constants. By the 1-second mark, their values were firmly established, a direct inheritance from the symmetry breakings of the first instance. These laws dictated how things would interact. They guaranteed that protons and neutrons would fuse into helium under those hot, dense conditions. They ensured gravity would act the way it does. This is the realm of inevitability, the clockwork machinery that produced the primordial element mix with such stunning precision. Alongside these laws, certain large-scale parameters of the cosmos were also fixed. The overall density of matter and energy, the expansion rate set by that density, and the critical balance between the forces, these were not random choices made at 1 second. They were the direct consequences of processes like inflation that had concluded moments before. So the universe's broad brush portrait, its overall composition and dynamic trajectory, was indeed determined. But then we come to the fine details, the specific masterpiece that will be painted on that vast, pre-stretched canvas. This is where inevitability meets chance. While the laws dictated how structure would grow, the exact where and what of that structure depended entirely on the initial seeds. Those seeds were the pattern of quantum fluctuations, the microscopic wrinkles in spacetime that inflation stretched to cosmic proportions. Their precise arrangement was not determined by any law. It was a frozen snapshot of quantum randomness. The universe at 1 second old contained the complete blueprint for its large-scale structure, but that blueprint was not a single, preordained design. It was one possible pattern drawn from a near-infinite set of equally valid patterns, all consistent with the same underlying physics. The subtle variations in density encoded in that blueprint would later, over billions of years, dictate where the first gravitational wells would form, pulling in hydrogen and helium to ignite the first stars. They decided which regions would become great galaxy clusters and which would become vast, empty voids. So was our current universe inevitable at 1 second old? The answer is both yes and no. The stage, the laws, the raw materials, and the script for how they would combine were all irrevocably set. But the specific set decoration, the placement of every galaxy, every star, and by extension, our own local cosmic address, was the product of a random quantum roll of the dice that had already happened. Our existence as conscious beings in a universe capable of fostering life was made possible by the fixed laws and constants. But our particular location in this cosmic story, the fact that we are here in the Milky Way and not in some other galaxy trillions of light years away, was written into a random seed. That random seed, the quantum blueprint for all structure, now entered a profound cosmic silence. For nearly 400,000 years after nucleosynthesis, the universe embarked on its long, dark childhood. The primordial soup of hydrogen and helium nuclei, electrons, and blinding light remained trapped in a thick, opaque fog. Photons, particles of light, could not travel any meaningful distance without crashing into a free electron, scattering endlessly in a dizzying pinball game. The cosmos was a glowing, featureless bank of mist, expanding and steadily cooling in the darkness. Then, a monumental transition occurred. When the universe reached the tender age of 380,000 years, it cooled to a critical threshold of about 3,000 degrees. At this temperature, electrons finally lost enough energy to be captured by atomic nuclei, forming stable, neutral atoms for the very first time, predominantly hydrogen and helium. This moment is called recombination. In an instant, the cosmic fog lifted. With electrons now bound into atoms, the paths of photons were suddenly clear. The light that had been trapped, scattering for eons, was finally set free to travel across the universe. This first flash of liberation is what we detect today as the cosmic microwave background, the CMB. It is the oldest light we can see, a baby picture of the cosmos taken when it was a mere infant. But here is the crucial revelation: that photograph was not taken at 380,000 years old. It was developed then. The film itself, containing every detail of the image, had been exposed and processed much, much earlier. The temperature of that light, its near-perfect uniformity, and most importantly, the faint, mottled pattern of hotter and cooler spots within it, those anisotropies, were not created at recombination. They were imprinted by events that concluded over 399,999 years before. The variations in temperature we see in the CMB map are direct photographs of the density seeds from the inflationary epoch, those quantum fluctuations stretched to cosmic size. They show us where the primordial soup was ever so slightly denser or thinner at the moment light was set free. The 1-second-old universe, with its fixed laws and its random seed pattern, had already determined exactly what this first snapshot would look like. Recombination was merely the moment the darkroom lights turned on, revealing a portrait that had been waiting in the developer bath since the dawn of time. The cosmic microwave background was more than a first photograph. It was a detailed instruction manual for the future. Etched into its faint temperature ripples were the precise coordinates for every great structure to come. For hundreds of millions of years, the universe remained a quiet, expanding sea of dark gas. But gravity never sleeps. It is the patient architect of the cosmos, and it had been handed a complete set of blueprints. Those subtle density differences from the inflationary seeds, now frozen into the distribution of matter, were the only invitation gravity needed. Where the primordial soup was slightly denser, gravity's pull was a fraction stronger. This drew in a little more of the surrounding hydrogen and helium from the neighboring, thinner regions. As more matter accumulated, the gravitational pull increased, drawing in even more material in a runaway process of cosmic construction. This was not a random or creative act, it was pure, deterministic mechanics. If you knew the exact pattern of the initial seeds and the laws of gravity, you could, in principle, compute what would happen next. The universe became a vast and slow-motion simulation, running a program written in the first second. The slightly overdense regions evolved into a magnificent web-like structure, the cosmic web. They formed great filaments of dark matter and gas, intersecting at dense nodes that would become galaxy clusters. The voids between them, the underdense regions, expanded into ever-growing empty spaces. Within those filaments, smaller knots of gas grew dense enough to collapse under their own weight, igniting nuclear fusion and sparking the first stars. These stars gathered into swirling proto-galaxies, which then merged and danced along the gravitational highways of the web. Every galaxy, every cluster, every filament in our observable universe today can trace its lineage directly back to a specific ripple in that ancient light. The formation of our own Milky Way, its specific location in a filament near the edge of a great void, was not an accident. It was the mathematically determined outcome of gravity acting on a particular set of initial conditions for over 13 billion years. This paints a startlingly deterministic picture from the 1-second mark onward. Once the quantum dice were rolled and their results inflated across the sky, the chain of causality was set. The laws of physics, acting on that specific seed pattern, dictated a single, unfolding future. It suggests that if some cosmic intelligence could have observed the universe at that 1-second birthday, with perfect knowledge of physics and the seed map, it could have predicted, in broad strokes, the entire history of cosmic structure. It would have foreseen the epoch of the first stars, the assembly of galaxies, and the eventual formation of a spiral galaxy in a particular filament where, billions of years later, a rocky planet would coalesce in its star's habitable zone. The universe's story, in its grand architecture, appears to have been a script read from a page written in its fiery youth. But this cosmic clockwork has a hidden flaw, a whisper of chaos woven into its grand design. The deterministic story of gravity sculpting the universe from its primordial seeds runs into a profound complication, one familiar from earthbound weather forecasts and fluttering butterfly wings. This is chaos theory, the mathematical understanding that in complex dynamic systems, even infinitesimally small differences in starting conditions can lead to wildly divergent outcomes over time. The universe, in its full, intricate glory, is arguably the most complex dynamic system of all. While the largest filaments and voids of the cosmic web may have been broadly predictable from the 1-second blueprint, the fate of any single knot within that web was not. Think of it like predicting the flow of a mighty river. You can be certain the water will travel downhill, carving a general path through the landscape. But can you predict the exact journey of one specific water molecule? Can you know which rock it will swirl around, which eddy will trap it for a moment, or which branch of a delta it will finally take to the sea? The molecule's path is exquisitely sensitive to every tiny bump on the riverbed, every gust of wind, every collision with another molecule. Its final destination is, in practice, unknowable from the start. The formation of galaxies, stars, and planets operates on a similar principle of sensitive dependence. The initial density seeds from inflation provided the gravitational starting points, but the process of building a galaxy is not a clean, solitary collapse. It is a violent, messy, and interactive ballet. Protogalactic clouds did not form in isolation. They jostled, merged, and cannibalized each other. The gravitational tug of a passing dwarf galaxy, the shockwave from a nearby supernova explosion, the subtle shearing forces from the cosmic web itself, these are all chaotic influences. A quantum fluctuation that was a trillionth of a percent stronger in one region at 1 second old could have meant a slightly denser gas cloud. That cloud might have collapsed into a star a few million years earlier than its neighbor. That earlier star's life and death, seeding space with heavy elements and shock waves, would then alter the environment for every star formation event that followed in that entire galactic neighborhood. Over billions of years, this chain of chaotic causality compounds. The difference between a spiral galaxy like our Milky Way and an elliptical blob could hinge on the timing and angle of a single major merger event, an event itself sensitive to minute initial variations. Zoom in further to our own solar system. The cloud that collapsed to form our Sun was one among billions in the Milky Way. Its specific composition, its spin, its eventual family of planets all resulted from a cascade of local conditions. A passing star's gravity could have stripped away material, preventing Jupiter from forming. A slightly different distribution of dust grains might have sent Earth into a different orbit, too hot or too cold for liquid water. The fact that we orbit a stable star, that Jupiter guards the inner system from comet impacts, that Earth sits in a narrow habitable zone, each of these is a happy accident in a long chain of chaotic events. From the perspective of 1 second after the Big Bang, our specific existence here was not just one possibility among many, it was an astronomically improbable one. The universe was destined to build structures and forge stars, perhaps even planets with the right chemistry for life. But the particular star we call Sun, the specific rocky planet we call home, and the exact evolutionary path that led to us were not written in the stars. They were written in the unpredictable, chaotic interactions between those stars. The grand script was set, but the fates of the individual characters were left to chance. This leaves us with a profound and unsettling question hanging in the air. If our specific cosmic address, our solar system, and our very existence hinge on a long chain of chaotic, improbable events, then why does the universe seem so perfectly set up for life in the first place? This is not about the placement of planets, but about the bedrock rules of reality itself. The fundamental constants of nature, those numbers fixed by the 1 second mark, appear to be suspiciously fine-tuned for our existence. Take gravity, for instance. The strength of the gravitational force seems calibrated with impossible precision. If it were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch long before stars could form. If it were slightly weaker, matter would never have clumped together, leaving a forever dispersed sterile mist of gas. The cosmos would be dark and empty. Or consider the strong nuclear force, the glue that holds atomic nuclei together. Its strength determines how stars burn and which elements are forged inside them. A few percent weaker and deuterium would be unstable, shutting down the nuclear furnaces of stars before they even ignited. A few percent stronger and protons would fuse too easily, burning up all the universe's hydrogen in a flash, leaving no long-lived stars to warm planets. Even the mass of the electron, a seemingly trivial number, is critical. If it were different by a tiny fraction, the chemistry that forms complex molecules, the very chemistry of life, would be impossible. The list goes on. It is as if someone dialed in dozens of independent, fundamental numbers on a cosmic control panel, each one landing in an extraordinarily narrow range that allows for galaxies, stars, planets, and ultimately observers. This eerie perfection is known as the fine-tuning problem. It forces us to confront a philosophical counterpoint to the clockwork determinism we've explored. If our local story was chaotic and chancy, perhaps the universal stage itself was not inevitable either. So how did we end up on a stage so perfectly set for our arrival? One compelling, though speculative, answer is known as the anthropic principle. In its simplest form, it states that we can only observe a universe that is compatible with our existence as observers. It is a selection effect. We are not seeing a universe finely tuned for life. We are life that has emerged in a universe capable of supporting it, and therefore we are, by necessity, asking questions in one of the rare cosmic neighborhoods where the numbers lined up just right. This logic leads to a staggering possibility, the multiverse. Imagine not one universe, but a vast, perhaps infinite, ensemble of universes, each with its own random set of physical constants and laws, born from eternal inflation or other cosmic mechanisms. In this breathtaking vista, every possible value for the strength of gravity, the mass of the electron, and the cosmological constant is realized somewhere. An overwhelming majority of these universes would be stillborn or barren, collapsing instantly or expanding into eternal emptiness. But in a vanishingly small fraction, the dials land in the golden zone. In those rare universes, stars shine, planets form, and life can arise. We, of course, find ourselves in one of those lucky ones. From this perspective, the fine-tuning is not evidence of design or inevitability, but of a cosmic lottery. Our universe's 1-second-old settings were not the only possible outcome. They were simply the winning ticket that allowed the question to be asked. The haunting precision of the constants becomes a postcard from a reality of unimaginable variety, whispering that our entire cosmos may be just one bubble in a frothing sea of alternative realities. The multiverse is not a single, tidy idea, but a sprawling landscape of possibilities born from our most ambitious theories. To understand it, we must first visit a refined version of cosmic inflation, the process that smoothed and seeded our own early universe. The theory of eternal inflation proposes that the inflationary burst that created our cosmos never truly stopped everywhere. Picture an infinite, bubbling pot of boiling water. Our entire observable universe is just one bubble that formed and stabilized within that eternally inflating medium. But outside our bubble, the inflationary energy continues to drive space to expand at a breakneck pace. In that raging sea, new bubbles are constantly nucleating at random, each one a separate universe with its own Big Bang. Crucially, when a new bubble universe forms, the inflationary field can settle into its stable state in different ways. This settling process is what determines the local laws of physics within that bubble, the values of its fundamental constants, and even the number of dimensions of space. In this breathtaking picture, our universe, with its specific gravitational strength and electron mass, is not special or unique. It is simply one frozen accident in an endless, frothing cascade of cosmic creation, where every possible set of physical laws is realized somewhere in the greater multiverse. String theory, a leading candidate for a theory of everything, paints a similar picture of profound plurality. In its framework, the fundamental constituents of reality are not point-like particles but unimaginably tiny, vibrating strings. The way a string vibrates determines whether it manifests as an electron, a quark, or a photon. But for this theory to work mathematically, it requires more than the three spatial dimensions we experience. It suggests there are additional, tiny, curled-up dimensions of space, perhaps 10 or 11 in total. How these extra dimensions are folded and compactified determines the effective laws of physics in the larger, observable dimensions. And here is the key: there is not just one way to fold them. The number of possible stable configurations is staggeringly large, estimated to be around 10 to the power of 500. Each configuration corresponds to a different vacuum state, a different possible universe with its own unique set of particles, forces, and constants. This is the string theory landscape, a vast, abstract terrain of possible realities. Our universe, then, is just one valley in this inconceivably gigantic landscape. The properties frozen into our cosmos at 1 second old were not the only possible outcome. They were simply the local topography of the particular valley our bubble of spacetime happens to occupy. This framework completely reframes the question of cosmic inevitability. If the multiverse is real, then our specific universe, with its 1 second old properties perfectly suited for life, was not predetermined in any meaningful sense. It was a single, random draw from an infinite cosmic lottery. The fine-tuning of the constants is no longer a mysterious coincidence begging for an explanation. It becomes a statistical necessity. In a sufficiently vast or infinite ensemble of universes, every possible combination of physical parameters will occur somewhere. The overwhelming majority of these universes will be sterile and lifeless, where atoms cannot form, stars cannot ignite, or complexity instantly collapses. But by the sheer law of large numbers, a tiny, fortunate fraction will, by pure chance, have all the dials set within the narrow habitable range. We could not possibly find ourselves in any of the dead universes. We can only arise and ask questions in one of the rare, bio-friendly ones. From this perspective, the profound predictability we saw from the 1 second mark onward, the clockwork nucleosynthesis and the gravitational unfolding of structure, was merely the local physics of our particular winning ticket. It was inevitable given our ticket, but the ticket itself was a random pick. The haunting question shifts from why our universe is the way it is to why we find ourselves in this particular one. And the answer, according to the multiverse, is simply because this is the only kind where beings like us could ever exist to ponder it. This elegant clockwork of the multiverse, however, rests upon a foundation of pure chance. To truly judge inevitability, we must peer beneath the cosmic machinery into the quantum bedrock of reality itself. Quantum mechanics is the rulebook for the universe at its smallest scales, governing particles, atoms, and the fields that fill empty space. And its central, unsettling lesson is this: at the fundamental level, nature is not deterministic. It is probabilistic. Consider a single, unstable atomic nucleus. According to the rigid clockwork laws of classical physics, if you knew everything about that nucleus, you could predict the exact moment it would decay. But quantum mechanics tells a different story. No amount of information will ever allow you to pinpoint the instant of its decay. You can only calculate a probability, a likelihood that it will happen within a certain window of time. When it finally does decay, the event is genuinely random, a spontaneous occurrence without a hidden cause we can uncover. This is not a limitation of our technology or understanding. It is a fundamental feature of the universe. The outcome is not predetermined. It is chosen in the moment from a menu of possibilities. This quantum randomness is not confined to a laboratory. It was woven into the fabric of our cosmos from its very first moments. Recall the inflationary epoch, that furious burst of expansion that set the large-scale structure of everything. What provided the seeds for that structure? Tiny quantum fluctuations in the inflating field. These were not minor imperfections in an otherwise determined process, they were the process. Inflation took these random, probabilistic events, these quantum jitters, and stretched them across the sky. The pattern of hot and cold spots in the cosmic microwave background, the blueprint for all galaxies, is therefore not a predetermined design. It is a frozen snapshot of quantum dice rolls that happened when the universe was a fraction of a second old. True inevitability was shattered in that instant. If we could rewind the tape of cosmic history back to the very beginning and play it forward again, the quantum fluctuations would not be the same. They would follow the same statistical probabilities, but their specific arrangement would be different. The resulting cosmic microwave background map would have a completely new pattern of ripples. The gravitational seeds would be planted in new places. As gravity worked its slow magic over billions of years, an entirely different cosmic web would form. Different filaments, different voids, different galaxies would emerge. Our Milky Way, our Sun, our Earth, they would almost certainly not exist in that alternative run of the universe. Their existence depends on a specific sequence of quantum random events that happen to turn out one way, but could have turned out in a near infinite number of other ways. This quantum wild card injects a profound and irreducible uncertainty into the heart of cosmic history. The laws of physics are not a script, they are more like a set of rules for a game of chance. They dictate the odds, the possible moves, and the consequences of those moves, but they do not dictate which specific move will be made at the quantum level. The universe, in its opening moments, played a game where every roll of the dice was real and irrevocable. The grand deterministic cascade we traced from the 1-second mark, from nucleosynthesis to galaxy formation, was always operating on a foundation of initial conditions that were themselves the product of chance. So when we ask if our universe was inevitable at 1 second old, we must confront this layered truth. The processes were inevitable given the laws, but the particulars, the specific configuration of matter and energy that led to us, were the magnificent and unlikely result of a quantum lottery whose numbers were drawn in the dark. Yet this quantum lottery, this cascade of chance, confronts a radically different vision of reality. There exists a perspective in physics and philosophy that dissolves the entire notion of becoming, of a universe that unfolds from past to future. It is called eternalism, or the block universe theory. In this view, time is not a river flowing from a source to a sea. It is more like a vast, frozen landscape. The past, the present, and the future do not come into being and then pass away. They all exist eternally and equally as fixed regions within a single, unchanging four-dimensional structure. Think of your own life not as a movie playing on a screen, but as the entire film reel itself. The frames of your childhood, this present moment, and every moment to come are all already there, printed on the celluloid. From a God's eye view outside this block, the universe at 1 second old, the era of the dinosaurs, the birth of our sun, and your reading of these words right now are all equally real. They are simply different coordinates along the time axis of a static cosmos. From this vantage point, the agonizing question of inevitability that we have wrestled with simply evaporates. It becomes meaningless. Asking if our universe was inevitable at 1 second old is like asking if a specific mountain on a map is inevitable. It simply is. The quantum fluctuations, the specific seed pattern, the formation of our galaxy, and every chaotic event that led to you, all of it is just the intricate, immutable topography of the block. There is no alternative timeline where the dice rolled differently, because every possible roll is just a different, unchanging part of a larger, perhaps infinite multiverse block. This is the ultimate expression of determinism, a cosmos where every event is eternally fixed in its relationship to every other, but it comes at a profound cost to our intuition. It challenges our deepest, most visceral experience, the feeling of a flowing present, the sense that the future is open and unwritten, the conviction that our choices matter. If the block universe is true, then free will becomes a compelling illusion, a story written in the neural pathways of a brain whose entire history, including this very thought, is a permanent fixture in the four-dimensional whole. The universe's story was not written as it went along. The entire book, from the fiery prologue to the final page, was always complete. We are merely turning the pages, discovering a tale that has, from a higher perspective, always been told. But if the block universe feels like a philosophical surrender, there is another, more provocative explanation for our finely tuned cosmic stage. It begins with a simple, startling question: what if our reality is not fundamental? What if the universe we experience is not the base layer of existence, but a construct, a detailed and immersive simulation running on some unfathomable computer in a higher-level reality? This is the simulation hypothesis, and it reframes our entire inquiry into a startlingly modern light. If our cosmos is a simulation, then the laws of physics are not discovered truths of nature, they are the programmed rules of the code. The fundamental constants are not mysterious numbers dialed in by chance. They are parameters set in a configuration file by the simulation's architects. And the initial conditions of the Big Bang, including the exact quantum seed pattern, were not the product of random quantum fluctuations, but the carefully chosen or algorithmically generated starting state loaded into the simulation's memory. From this perspective, the moment we have been fixated on, the universe at 1 simulated second old, takes on a completely different character. It was not a moment of cosmic becoming. It was a calculated data state, a specific frame in a pre-rendered sequence, or the output of a deterministic algorithm running its course. Within the logic of the simulation's programming, everything that followed from that 1-second timestamp was perfectly inevitable. The fusion of hydrogen into helium, the formation of galaxies along the seeded coordinates, the evolution of life on a planet like Earth, all of it would be the inexorable output of the code executing without error. The apparent quantum randomness we observe could simply be a sophisticated pseudorandom number generator, creating the illusion of indeterminacy to make the simulation seem more rich and natural, while still being perfectly predictable to the programmers who know the seed value. In such a reality, our entire history, from the first femtoscon to this very moment, could be seen as a single, enormous calculation. The feeling of free will, the agony of choice, the thrill of the unexpected, all would be part of the immersive experience, scripted or generated in advance. The simulation argument does not prove this is true, but it offers a chillingly coherent framework for why our universe appears to have such a rigid mathematical backbone. It suggests that the haunting predictability we traced from the first second might not be a feature of a fundamental reality, but a signature of a designed one. We are left to wonder, are we uncovering the deep laws of nature, or are we reverse engineering the source code of our own existence? These grand ideas, from quantum dice to simulated realities, might feel untethered from the world we can touch and measure. Yet the truth is, we are not speculating in a vacuum. The universe has left behind tangible evidence, cosmic fossils from its fiery infancy, that we can examine here and now. The most profound of these relics is the cosmic microwave background, that ancient light set free when atoms first formed, but it is far more than a baby picture. It is a forensic snapshot of the universe as it was at 380,000 years old, and by extension, a coded message from its very first second. The near-perfect uniformity of that background glow is the direct signature of inflation, the event that stretched a microscopic region smooth, and the tiny, specific pattern of hotter and colder spots within that glow. Those are the fingerprints of the primordial quantum seeds blown up to cosmic scale. By meticulously mapping these temperature variations with satellites, cosmologists are not just looking at a static image. They are reading the initial conditions, the very blueprint that gravity would follow for billions of years. They can compare the statistical properties of this pattern against predictions from different models of inflation, testing which version of that explosive genesis best matches our reality. It is a direct archaeological dig into the moment the cosmic dice were cast. Another set of fossils is written in the oldest stars. The primordial abundance of the light elements hydrogen, helium, lithium, and their isotopes acts as a cosmic receipt from the first 3 minutes. The precise ratios we measure in pristine interstellar gas and ancient stellar atmospheres match, with stunning accuracy, the predictions of Big Bang Nucleosynthesis. This tells us that the nuclear physics we understand today was already in full deterministic effect when the universe was just 1 second old. The density of ordinary matter, the neutron-to-proton ratio that froze out at that moment, they are all encoded in that elemental mix. It is a chemical timestamp proving the clockwork was already running. Finally, we have the grand architecture of the cosmos itself. The vast cosmic web of galaxies and voids, mapped in 3 dimensions by ambitious sky surveys, is not a random splatter. Its statistical properties, the sizes of clusters, the lengths of filaments, the distribution of matter are the grown-up version of the infant pattern in the cosmic microwave background. By running the laws of gravity and cosmology backwards in sophisticated computer simulations, starting from the CMB seeds, scientists can see if they evolve into a universe that looks like the one we observe today. And they do with remarkable fidelity. This process is like watching the film of cosmic history in reverse, from the present-day web of galaxies back to the CMB snapshot, and finally to the inflationary seeds that started it all. Each of these fossils, the light, the elements, the structure, serves as an independent check on the others, building a consistent and testable story of the universe's first moments. So what do these fossils tell us about inevitability? They confirm that the framework was set with incredible precision. The laws, the constants, the expansion rate, they were all locked in and operating as a predictable engine from at least the 1 second mark onward. The cosmic film, once started from that specific frame, runs forward with deterministic force, but the fossils also preserve the indelible mark of randomness. The specific pattern in the CMB, the unique arrangement of galaxies, these are the artifacts of quantum chance. They tell us that while the movie had to follow the laws of physics, the exact plot, the placement of every star, every planet, every potential observer was one of countless possible scripts. Our observable universe, in all its glorious, intricate detail, is therefore both a masterpiece of inevitable physical law and a singular, frozen accident of quantum probability. We are the outcome of a perfect storm where rigid necessity met fundamental chance. Our cosmic story could have been so very different. Let's play a game of what if, rewinding the tape to that 1 second birthday and giving it the gentlest of nudges. Suppose we reach into that searing plasma and adjust a single dial, turning the strength of gravity up by just 1%. The change seems trivial, but in the delicate balance of the early cosmos, it is catastrophic. A slightly stronger gravitational pull means the universe's expansion slows more quickly. The great tug of war between outward momentum and inward pull tips decisively. Instead of coasting for billions of years, allowing galaxies to form and stars to ignite, the entire cosmos grinds to a halt much sooner. The universe reaches its maximum size, perhaps only a fraction of its current scale, and then begins to contract. A great cosmic reversal begins, a backward rush into a fiery oblivion known as the Big Crunch. All structure is erased, all potential for complexity snuffed out in a final, uniform inferno. In this universe, there is no cosmic microwave background to map, no ancient stars to study, and certainly no one to wonder about its brief, tragic life. Our existence depends on gravity being weak enough to allow for a long, fertile expansion. Now, let's reset the clock and try a different tweak. This time, we leave gravity alone but alter the properties of matter itself. We make the neutron just a fraction of a percent lighter relative to the proton. Remember, that tiny mass difference was critical. It dictated how many neutrons were available to build atomic nuclei when the universe was a few minutes old. If the neutron is even slightly lighter, it becomes far more stable. Fewer neutrons decay into protons in that first second. The frozen neutron-to-proton ratio is now much higher. When Big Bang Nucleosynthesis begins, nearly all these extra neutrons get bound into helium nuclei. The problem is, helium is a nuclear dead end under those early conditions. The chain reaction stops there. With almost all the neutrons consumed in a helium-making frenzy, there is little or no hydrogen left over. Hydrogen, a single proton, is the universal fuel for stars. Without it, the cosmos is filled with inert helium gas. When the first gravitational clumps form, they have nothing to burn. No hydrogen means no sustained nuclear fusion, no long-lived stars to warm planets, and no way to cook the heavier elements like carbon and oxygen that are the building blocks of life. The universe becomes a dark, cold graveyard of failed stars, a silent expanse of unlit helium balloons. For a final twist, imagine adjusting the initial density of the universe, making it a bit higher than it was. This parameter was set by the details of inflation, the energy of the quantum fields that drove that explosive growth. A denser early universe expands faster at first, but that extra mass also means more gravitational pull. The delicate dance between expansion and contraction becomes a stumble. The universe might still expand for a time, but structure forms too rapidly and too violently. Matter clumps into enormous, monstrous black holes almost immediately, swallowing the primordial gas before it can settle into graceful galactic disks. Alternatively, if the density is too high by just the right amount, it could trigger a phase transition, a sudden and catastrophic rearrangement of the vacuum of space itself. This could rip the fabric of space-time, creating bubbles of destruction that expand at the speed of light, erasing everything in their path. In either scenario, the orderly, gradual construction project that built our cosmic web is replaced by chaos or annihilation. These thought experiments are not just whimsical fantasies, they are stress tests for our understanding of reality. They reveal a profound truth we have been circling all along. The rigid processes of nuclear fusion and gravitational collapse were indeed set in stone by the 1-second mark. The universe had to make elements and it had to build structure. But the specific, life-allowing outcome we enjoy, a universe with long-lived stars, abundant hydrogen, and stable planets, was not guaranteed by those processes alone. It was contingent, dependent on a very precise and seemingly fragile set of initial conditions. Tweak one number by a hair's breadth, and the entire edifice of complexity crumbles. We are not the inevitable product of a clockwork cosmos. We are the breathtakingly rare guests at a banquet where every ingredient had to be measured with perfect, inexplicable care. Physics has always been a battleground for two ancient titans, fate and chance. On one side stands the ghost of Pierre-Simon Laplace, the 18th century mathematician who envisioned a universe of absolute determinism. He proposed that a supreme intellect, knowing the precise position and momentum of every particle in the cosmos, could calculate the entire future and past with perfect accuracy. In this clockwork vision, everything from the orbit of a planet to the flutter of a thought is merely the unfolding of a script written at the dawn of time. The universe's 1-second birthday, in this view, was not a beginning but a single, fixed frame in a film that was already complete. The opposite pole is defined by Werner Heisenberg and the quantum revolution. His uncertainty principle shattered the dream of perfect predictability at the most fundamental level. It revealed a universe built on probability, where events at the smallest scales are not caused but chosen from a menu of possibilities. This is a cosmos where genuine novelty and spontaneity are woven into the fabric of reality. The quantum seeds of our galaxies were not pre-placed, they were the result of a roll of dice. So which vision won? The profound insight of modern cosmology is that neither did, or rather, both did in a strange partnership. The universe presents us with a profound hybrid. It is a cosmos of rigid, deterministic laws operating on a substrate of random initial conditions. Think of it as a game of pool played on a perfect, frictionless table, where the laws of physics dictate exactly how the balls will roll and collide once the cue ball is struck. The outcome of any collision is perfectly predictable, but who struck the first ball and from what exact angle with what precise spin? That initial break shot was the quantum fluctuation of the inflationary epoch. Its specific configuration was not determined by the laws of the pool table, it was a random event. Once that break occurred, however, the ensuing cascade of collisions followed an inevitable, calculable path. This is the precise nature of our cosmic story. At 1 second old, the universe had already executed its break shot. The values of the fundamental constants were locked in, the expansion rate was set, and the nuclear recipe book was open. The laws of gravity and nuclear physics, like the perfect geometry of the pool table, guaranteed a certain range of outcomes. Stars would form, elements would be forged. Structure would grow, but the exact detailed future, the specific arrangement of every galaxy, the location of every star, the existence of our particular solar system, was not written in a single, inevitable line. It was one possible trajectory within a vast fan of possibilities, all consistent with the same unbreakable rules. Our reality is the breathtaking product of this marriage, where necessity provides the stage and chance provides the specific, glorious play that unfolds upon it. This cosmic lottery extends right down to our own backyard. The grand architecture of the universe may have been sketched in its first second, but the story of our pale blue dot and the life upon it reads like a series of fortunate escapes and random rolls of the dice. Consider the formation of Earth itself. Our solar system coalesced from a swirling disk of gas and dust around a young sun. The specific arrangement of planets we see today, with Jupiter in its distant guardian orbit and Earth nestled in the habitable zone, was not guaranteed. It was the outcome of countless chaotic interactions, gravitational nudges, and collisions between planetesimals over millions of years. A slightly different distribution of mass in that primordial disk, or a passing star's gravitational tug at just the wrong moment, could have sent Earth spiraling into a lethal orbit or ejected it from the system entirely. Our stable, life-nurturing platform was a prize won in a chaotic game. This randomness only intensifies when we turn to the story of life. The universe, through its fine-tuned constants, made chemistry possible. It forged the carbon in our bones and the oxygen in our lungs inside ancient stars. It provided the raw ingredients, but the recipe for life, and especially for intelligent, self-aware life, was not written in the stars. It was dictated by evolutionary contingency, a relentless sequence of chance events where every fork in the road could have led to a completely different destination. The history of life on Earth is a tapestry woven with threads of sheer accident. A random genetic mutation grants a microbe resistance to a changing environment. A volcanic eruption opens new ecological niches. A predator fails to catch its prey, allowing a new lineage to flourish. The most dramatic example hangs over our entire existence. 66 million years ago, a mountain-sized asteroid, a random piece of cosmic debris left over from the solar system's violent construction, struck the Yucatan Peninsula. The impact unleashed global firestorms, a years-long winter, and mass extinction. It was the end for the dinosaurs, the dominant rulers of the planet for over 150 million years. Their demise was not fated, it was bad luck on a planetary scale, yet that catastrophe was our opportunity. It cleared the stage for small, scurrying mammals to emerge from the shadows and eventually diversify into every form we see today, including the primate lineage that would lead to us. Without that random, devastating impact, the dinosaurs likely would have continued their reign, and intelligent mammals might never have arisen at all. Even within our own direct lineage, the path to Homo sapiens was narrow and meandering. Countless hominid species evolved, competed, and went extinct. Our existence hinges on a specific series of climatic shifts in Africa, on successful migrations out of the continent, and on a cascade of cognitive and social adaptations that could have easily unfolded differently. A slight change in climate patterns 200,000 years ago might have stranded our ancestors in an isolated valley, leading to their extinction. A different social structure might have prevented the development of complex language and culture. We are not the pinnacle of a predetermined evolutionary ladder. We are the survivors of a long, chaotic, and bloody game of elimination, where the rules changed with the weather and the roll of the genetic dice. So where does this leave us in the grand narrative? The universe, through its laws and constants, created a stunningly rare arena where life could eventually emerge. It built the stadium and set the basic rules of physics and chemistry. But it did not write the play. The emergence of our specific planet, the evolution of life, and the rise of a species capable of contemplating its own origins were not guaranteed outcomes. They were a chain of increasingly improbable accidents within that vast arena. We are the product of a double lottery. First, the cosmic lottery that produced a bio-friendly universe with the right constants, and second, the planetary and biological lottery that, against staggering odds, produced us. Our existence is a testament not to cosmic inevitability, but to the breathtaking power of chance within a framework of possibility. We are not the universe's intended conclusion. We are its most fascinating and perhaps most fragile surprise. This dizzying chain of cosmic and biological luck brings us to a humbling frontier. For all the breathtaking certainty we have traced from that 1-second mark, our story is built upon pillars of profound mystery. The universe we can see and measure, the one made of atoms, stars, and galaxies, accounts for less than 5% of its total content. The remaining 95% is a complete enigma, a darkness that may hold the ultimate keys to our cosmic fate. We call these shadows dark matter and dark energy. Dark matter is the invisible scaffold. Its gravitational pull is what holds fast-spinning galaxies together and binds great clusters in the cosmic web. Without its unseen embrace, galaxies would fly apart. We know it is there because of how it bends light and tugs on stars, but we have no idea what it is made of. It is not any known particle. It is a ghost in the machinery, a silent partner whose nature remains utterly unknown. Dark energy is even more strange. It is not matter at all, but a property of empty space itself, a repulsive force causing the expansion of the universe to accelerate. Its discovery in the late 1990s was a shock, revealing that the cosmos is not just expanding, but flying apart faster and faster as time goes on. We can label it and measure its effect, but its origin is a complete mystery. Is it a constant energy woven into the vacuum, or a dynamic field that could change over time? The answer dictates the ultimate fate of everything, whether the universe will expand forever into cold, thin darkness or tear itself apart in a distant future. These are not minor gaps in our knowledge. They are vast, yawning chasms in our understanding of reality. Our confident tracing of causality back to the first second is a story told only about the luminous 5%. The true directors of the cosmic play, dark matter and dark energy, remain anonymous. Their properties, set in those first instants, would have fundamentally shaped everything that followed, yet we are still guessing at their identities. Our ignorance runs deeper still into the very genesis of the cosmic blueprint itself. We speak of inflation as the event that stretched quantum seeds into cosmic ones, but we must confront a startling admission. We do not know what triggered inflation, what powered it, or what made it stop. The theory beautifully explains the universe we see, but the engine behind it is pure speculation. What was the inflatoned field? How did it get its immense energy? Why did it decay in just the right way to produce our specific universe? These questions strike at the heart of our origin story. Without answers, the moment we call the beginning is itself shrouded in fog. Even more fundamentally, our entire narrative hits a wall at the Planck epoch, that first 10 to the negative 43 seconds. To understand what truly happened at time zero, we need a theory of quantum gravity, a framework that unites Einstein's theory of general relativity, which governs the very large, with quantum mechanics, which governs the very small. In that first unimaginable flash, the universe was both incredibly massive in density and incredibly tiny in size. Our two great pillars of physics become mutually incompatible. Relativity says spacetime is a smooth, curving stage. Quantum mechanics says that at the tiniest scales, that stage must be a frenzied, probabilistic foam. We currently have no language to describe a reality where both are true. Was there a singularity, a point of infinite density, or did the universe emerge from a quantum fluctuation in some prior state? Our equations simply break down. This means our ability to trace causality back to the absolute beginning is not just difficult, it is currently impossible. The chain of if this, then that we have so carefully followed reaches a point where this is utterly unknown. So where does this leave our central question? Was our universe inevitable at 1 second old? With our current knowledge, the most honest answer is that we do not yet know enough to say. The clockwork predictability of nuclear fusion and gravitational structure formation is undeniable, but it operates within a theater whose foundations are hidden. The true answer to inevitability may lie in the physics we have not yet discovered. Perhaps a future theory of quantum gravity will reveal that the constants of nature, the balance of dark matter and dark energy, and even the trigger for inflation are all the unique, necessary outcomes of a single, elegant mathematical principle. In that case, our universe truly was the only possible universe from the first moment of coherent physics. Or the opposite may be true. The new physics might show us a landscape of even greater randomness, where the properties of our cosmos are the result of a quantum selection so vast it makes our current multiverse ideas seem simple. The dark sectors may be filled with their own rich physics and history, adding layers of chance we cannot yet perceive. Our 1 second old universe, with its set constants and frozen seeds, would then be just one possible configuration within a much deeper and more chaotic genesis. This is the thrilling, unfinished nature of cosmology. Every answer unravels new and deeper questions. The story we have pieced together from the cosmic microwave background, from ancient stars, and from the galactic web is the most compelling one we have. It tells us that from a certain point onward, the universe ran like a magnificent, predictable clock. But whether that clock was wound by necessity or by a random hand in a deeper dark is a mystery that still lies ahead of us, waiting in the shadows of the unknown. The universe at that 1 second birthday was a masterpiece of constrained possibility. Its physical laws were now the unbreakable rules of the game, written into the fabric of reality during those first explosive instants. The strength of every force, the mass of every particle, the very speed of light, these were no longer variables, they were fixed numbers on the cosmic control panel. With those numbers set, the broad trajectory of our cosmos became not just likely, but nearly certain. The geometry of space, the relentless expansion driven by the afterglow of inflation, and the precise recipe for cooking hydrogen and helium in the first 3 minutes, all of this was on a predetermined course. A hypothetical physicist from that era, armed with perfect knowledge of the constants, could have calculated the future in stunning detail. They would have predicted a universe expanding for billions of years, cooling into darkness, and filled with a primordial fog of precisely 75% hydrogen and 25% helium. The stage, in its grandest dimensions, was irrevocably set, but the stage was still empty. The specific drama that would play out upon it was an entirely different matter. While the laws dictated how matter would behave, they did not dictate where it would be. The distribution of that primordial matter, the subtle hills and valleys in the density of the cosmic soup, was not a product of law but of chance. Those variations were the frozen imprint of quantum randomness from the inflationary epoch, a unique pattern of ripples that could have been arranged in a near infinite number of other ways. This is the crucial synthesis. The universe's fate was bifurcated into two realms. In one realm lived inevitability, the domain of physical law. Gravity had to pull. Nuclei had to fuse under those conditions. The cosmic film, once this specific frame started rolling, had to follow the script written by the constants. In the other realm lived profound contingency, the domain of initial conditions. The exact placement of every density seed, which would later blossom into a galaxy cluster or fade into a void, was a singular accident. So, was our universe inevitable at 1 second old? The answer is both resounding and nuanced. The cosmos we inhabit was probable, given the laws. A universe with galaxies, stars, and the chemical ingredients for planets was a highly likely outcome of those fixed rules playing out over time. But our particular cosmos, with the Milky Way positioned exactly where it is, with our Sun forming in this specific spiral arm, and with Earth orbiting in its precise Goldilocks zone, was not predestined. It was one exquisite possibility actualized from a sea of others. Our existence is therefore built on a foundation of both ironclad necessity and breathtaking accident. We are the children of a universe that had to become complex but did not have to become us. This realization carries a profound weight, reshaping our very sense of place. If our universe was not meticulously preordained, does that diminish our significance? The answer is not a simple yes or no, but a shift in perspective. We are not the central characters in a story written solely for us, the inevitable climax of a cosmic plan. That can feel unsettling, like being demoted from a starring role to a walk-on part. Yet this very randomness bestows a different, more precious kind of meaning. Our existence is not a foregone conclusion, but a gift of staggering improbability. Every atom in our bodies was forged in stars that formed because of a specific quantum seed. Our planet exists in a stable orbit because of a chaotic series of events in a dusty disk. We are here because of a chain of accidents spanning 13.8 billion years, a chain that could have broken at any link. In a universe of pure inevitability, we would be mere spectators watching a film whose ending we already know. In this universe of chance, we are active participants in a story still being written, a story that did not have to include us at all. That makes our presence not insignificant but astonishingly rare and valuable. It transforms the cosmos from a cold machine into a grand, ongoing narrative where our chapter, however brief, is a genuine surprise. This understanding also reveals the true power and purpose of science. If everything were perfectly predetermined from the first second, science would merely be the act of reading a script already written. There would be no mystery, no discovery, only revelation. But a cosmos built on a foundation of chance is one brimming with genuine questions. Why do these constants have these values? What is the nature of the dark sectors? How did life emerge from non-life? These are not puzzles with a single, pre-loaded answer. They are real explorations into the unknown. Science becomes a heroic endeavor, our method for mapping a territory that was not designed for us to understand, but which we can understand through curiosity and reason. It is a dialogue with a universe that is complex, contingent, and full of secrets waiting to be uncovered. This preserves a cosmos that is fundamentally creative and rich with novelty. History is not an illusion, it is the accumulation of unique events, each one shaping the next. The formation of Earth, the extinction of the dinosaurs, the rise of humanity, these are not lines in a predetermined play. They are the actual, contingent turns that made our present moment possible. It means every detail around us, from the pattern of frost on a window to the specific arrangement of stars in the night sky, is a unique artifact of an unrepeatable history. We live in a universe where things genuinely happen, where the future is open within the bounds of physical law, and where our choices on our small planet add new threads to this magnificent, chancy tapestry. Our place, therefore, is not at the center of a clockwork. It is as witnesses and storytellers in a cosmos of endless, beautiful accident. From the unimaginable frenzy of the Planck epoch to the silent forging of the first atomic nuclei, our journey has traced the universe's first heartbeat. We have seen how the separation of forces, the explosive stretch of inflation, and the delicate asymmetry between matter and antimatter built a stage with rigid, unbreakable laws. By the time the cosmos was 1 second old, its broadest strokes were indeed set in stone. The fundamental constants were locked in. The recipe for hydrogen and helium was written. The engine of gravity was primed to sculpt a cosmic web from the seeds inflation provided. In its general character, a universe of structure and complexity was not just possible, it was the nearly inevitable outcome of physics taking its course. Yet for all that magnificent clockwork, the exquisite details of our reality were never guaranteed. The specific pattern of those primordial seeds was a quantum accident. The chaotic dance that placed our sun in a quiet spiral arm, that guided a rogue asteroid to reset life's course, that allowed a particular lineage of apes to gaze upward and wonder, these were rolls of the cosmic dice. We are the product of a profound partnership between ironclad law and fundamental chance, so we find ourselves here on a pale blue dot contemplating our origins. Our existence is not a preordained line in a script read from the first second. It is a gift of staggering improbability, a story still unfolding. We are not mere spectators in a predetermined play. We are the universe itself, become conscious, looking back at its own fiery birth and forward into its unknown future. We are active participants in a grand, ongoing narrative, born from a moment of both necessity and beautiful accident. What does that mean for you? Does this dance of fate and randomness make our story more meaningful or more fragile? Share your thoughts in the comments below.